Well, good evening. I'd like to welcome everyone to our Spring 2013 Sigma Xi National Lecture. I'm Lee Burris, and it's my distinct privilege to introduce our speaker. As you can see from the screen, our speaker is Richard Anthus, President Emeritus of the University Corporation for Atmospheric Research. Dr. Anthus is a native of Missouri, spent much of his early life in Virginia. He's a graduate of the University of Wisconsin-Madison, where he earned his BS, MS, and PhD, each in meteorology. Following his PhD, he joined the Pennsylvania State University as a faculty member, where in less than 10 years he was promoted to professor. He stayed there till 1981, when he left Penn State to go to the National Center for Atmospheric Research in Boulder, Colorado. And he spent a subsequent time in his career in Boulder, initially with the National Center for Atmospheric Research, and more recently with UCAR, the University Corporation for Atmospheric Research. Dr. Anthus, as you would expect, has a distinguished career. As with any of this speaker with Sigma Xi, has a very impressive vita. He's published more than 100 papers. He's been very active. He's a fellow in the American Meteorological Society. I'm having to cheat at the moment and read things. He's a winner of the American Meteorological Society's Clarence L. Emsinger Award for promising atmospheric scientists, especially in researching tropical cyclones. He's a holder of the Jules G. Charney Award for sustained contributions in theoretical and modeling studies. He's a fellow in the American Geophysical Union, and perhaps a really even more noteworthy award than those is he received, in 2003, he received the Friendship Award from the Chinese national government, which is an extraordinarily competitive and impressive award. So I could continue with that, but you're really not interested in having me speak about Dr. Anthus. We're really much more interested in hearing him speak. So Dr. Anthus, please, the floor is yours.
Okay, thanks very much, Lee, and thanks to Sigma Xi for inviting me. Given the later start than I usually give lectures, I've shortened this to 3.5 hours. So I promise you, even if I go over a little bit, we'll be done by midnight for sure. The title of my talk is Demons and Butterflies, Weather Predictability and Predictions. And you'll see what all this will become clear to you if it's not already. I'm going to give a prologue during which I will say almost nothing. It's a pictorial essay of Hurricane Sandy. And you will see the relevance of good predictions, I think, more forcibly if I just show these slides 2 seconds apart without any comment whatsoever. I was certainly surprised when I first saw it. I follow hurricanes closely. My wife and I were on the East Coast during Sandy, south of the storm's landfall, and I had no idea of the real devastation until I saw this series of photographs which were put together by my good friend and colleague Mel Shapiro. So I will just be quiet for the next couple of minutes and let you in silence see these incredible pictures of the devastation of Hurricane Sandy. And then I think there's some lessons I will draw from that are relevant to predictability and predictions. So here we go. Okay, so I think that gives you a feeling that statistics and words can't give. This isn't really the topic of the talk, but I thought it was a cover on the Bloomsburg Business Week, and that this is a whole other subject which I won't get into tonight. But a few statistics on Hurricane Sandy, a.k.a. Superstorm Sandy and Frankenstorm. It formed in the Western Caribbean on October 22nd, very late in the season for a tropical cyclone. It made landfall in New Jersey at 8 p.m. Monday, October 29th. A week later, It was the largest Atlantic hurricane on record. Not the most intense, but the largest, meaning the diameter of the circulation, the diameter of the clouds. At least 253 people were killed, and at least $74 billion in damage, which is about equal to the much discussed sequester. So a huge economic impact in this one storm. And I'll get back to that 253 people killed in a minute. How good were the forecasts? This is a talk on forecasts, predictability, and predictions. Well, they were excellent. Then the question I have for you is how many more lives would have been lost without the good forecast? And I've been have no way of knowing this, of course, but I'm guessing it would be thousands rather than 253 people. I gave this talk at the Oregon State University last week. A person came up afterwards and said that she thought that the thousands was probably an underestimate. It probably might have been tens of thousands of people. And that's because so many people were in harm's way and were out of harm's way by the time this thing hit. There was warnings of at least 3 days, and there was massive evacuations. People moved inland instead of being in all these houses. I gave a similar talk at Fairfield University, which is in Fairfield, Connecticut, right on Long Island. And there's houses, summer houses that wealthy people go to during the from New York go to during the summer, and these houses are vacant during the well, they're not vacant. They're used by students. They're rented by students during the winter season. Winter season being after Labor Day until Memorial Day. And so there were probably 600 students in these houses. You know how students crowd into places to save rent, and it's right on Long Island. This area was totally evacuated, mandatory evacuation. They got everybody out of these houses. All the students were taken off. Some of those houses were dragged into the ocean, totally demolished. All were severely flooded. I would have guessed just this one little settlement alone would have been probably 500 young people would have been washed out to sea. So incredibly important that the forecasts were accurate and people heeded them. Thousands instead of 250. 250 is not great if you're one of those family members, but it sure beats 25,000 or something like that. So forecasts are really important. Forecasts, and these storms happen in different parts of the country all the time. And so that's just to set the context how important this is. Now, why were these forecasts so good? That's kind of a lesson I'll probably repeat it several times. Forecasts were good because modern meteorology is science, not folklore, not based on statistics, but based on mathematics, physics, satellite observations. And these systems are almost all funded by the U.S. government. And the government has funded these systems and development for over 50 years. Much of the research was done in universities, including universities like Iowa State. And so if you hear people saying that government is too big, it's worthless, it wastes its money, think about Hurricane Sandy and the thousands of lives that were saved by the government-sponsored research, the government-sponsored satellites, the government-sponsored computer models, and the research done in our great universities around the country. So that's one kind of take-home message. Never before had a hurricane approached the East Coast from the east in late October. That's just how unusual it was. And this shows the track. And I'm not sure I have a pointer here. There's a red button, but I'm not sure I want to push it. So you can get the idea here. The Hurricane Sandy is labeled Sandy. That's the storm that comes up off the coast of Hatteras and then makes that left hook and goes inland. All the other hurricanes of Category 2 that pass within 200 nautical miles of New York City for the last 150 years. As you can see, we're moving to the northeast. If they made landfall at all, they just brush the coast. So Hurricane Sandy just stands out like a sore thumb. So any method based on folklore, experience of forecasters, statistical methods, empirical methods would have all failed because it had never happened before. And yet, this storm was forecast more than a week ahead of time. Now there are 3 panels here. This is from the European Center for Medium Range Weather Forecasting in Europe. It's the best weather forecasting center in the world. On the left shows the forecast probability of a windstorm 9.5 days before landfall. And you can see that already 9.5 days before a storm had even formed, there was a highlighted area of possibility of heavy winds 9.5 days before the landfall. And then the middle panel shows a series of tracks that were forecast by the model, and it's the so-called ensemble of forecasts. You see that many of them, if not most, did indeed predict that left hook making landfall along the east coast, and the actual storm of Sandy is on the right. So this was indication, the forecast was made of something like Sandy 2 days before the storm even formed, much less the storm had formed and they were just forecasting the track. So they forecast the formation of the storm 2 days before it occurred, and then the subsequent track in a track that had never before been observed. And that's all based on science, basically a hands-off operation based on computer models and observations that go into these models. So, that's the prologue. You thought that was the talk, right? Well, now we'll get into some more history and some more fanciful, and I guess this one worked. Now, I'm going to, I have to click this one. It's one of the few. Animations I have to interfere with. So somewhere in a jungle in Brazil, this is going on right now. It's okay. So butterflies and demons. What's the significance of butterflies, which you saw in the jungle in Brazil, and the demon that you saw? It's my friend Mel Shapiro, who did the nice photo essay from you. Well, foretelling the future has always been a fascination of humanity, and prophets over the ages have been worshipped and vilified. It's not just weather forecasting, but forecasting, foretelling the future of everything. It's just a fascination of human beings. And these are all, of course, ways of expressing how we look at foretelling the future. The last one was one kind of fast, but said that all predictions are based on observations. And I can say that all good predictions are based on observations. I can't think of any predictions that are not scientifically based, that are not based in some sense on observations. So, what about predictability and prediction? Well, the idea of prediction and foretelling the future goes back many, many hundreds of years. And Gottfried Leibniz, who lived from 1646 to 1716, said that everything proceeds mathematically. If someone could have sufficient insight into the inner parts of things, and in addition had remembrance and intelligence enough to consider all the circumstances and take them into account, he would be a prophet and see the future in the present as in a mirror. Now, what he's saying is that if I completely understood life, and life is chemistry, basically, biology, and if I knew every one of your brains and how they worked and how you'd react to stimuli of various kinds, everybody in the world, all 7 billion, and I knew how the butterflies flapped. I knew everything about the world. I could predict what's going to happen 500 years from now. I could predict how many children you're going to have, how many children they're going to have. That's the extreme of what he's saying, but that's basically what he's saying. That's a philosophical question, obviously. And it's a good thing to just have fun talking about how much can we know and how far will that take us into predictions. Well, similar ideas followed. The Marquis de Laplace dreamed of an intelligent being, an intellect, which he called an intellect, and was later dubbed Laplace's demon, who knew the positions and velocities of every single atom and used Newton's equation of motion to predict the future of the entire universe. And he said, this is a quote, "We may regard the present state of the universe as the effect of its past and the cause of its future. An intellect which at any given moment knew all the forces that animate nature and the mutual positions of the beings that compose it, if this intellect were vast enough to submit the data to analysis, could condense into a single formula the movement of the greatest bodies of the universe and that of the lightest atom, for such an intellect, nothing would be uncertain, and the future, just like the past, would be present before its eye." So this is a physical universe kind of statement. It doesn't get into the prediction of people and animals and how the biology would respond, but it's a physical one. If we knew all the atoms and knew the laws that govern all the atoms, we could predict the future of the universe. Now, this is surprisingly a good description of how numerical weather prediction works. Because numerical weather prediction, we try to know the positions of all the storms, all the high-pressure systems of the entire atmosphere, the oceans, which interact with the atmosphere. And we try to use Newton's law mathematically to move these systems ahead in time and forecast their future. It's really exactly what he's saying. We do it for weather. We don't go much beyond weather. We don't go into the forecast of the universe and certainly not forecast of people. But this is pretty much what we do in numerical weather prediction. So it's observations, knowing the present, and knowing the laws that govern the fluid, which we call the atmosphere, and the fluid, which we call the oceans, and how they interact in a very deterministic, predictive way. And I'll keep coming back to this as I go along. But then there's some skeptics. Niels Bohr, you can read it here. It sounds to me it's like something Yogi Berra would have said, and he probably might have said it. So, more relevant to meteorology, one of the greatest early meteorologists of all times, Wilhelm Bjerknes, a Norwegian, resaid what Laplace said with direct relevance to meteorology. He said, if it is true, as any scientists believe, that subsequent states of the atmosphere develop from preceding ones according to physical laws, one will agree that the necessary, sufficient conditions for a rational solution of the problem of meteorological prediction are the following. 1 and 2. 1 is one has to know with sufficient accuracy the state of the atmosphere at a given time. These are the initial conditions, what we call the initial conditions. And 2, one has to know with sufficient accuracy the laws according to which one state of the atmosphere develops from another. So number 1 is observations. We have to observe the atmosphere at some initial time. And number 2 is solving the appropriate equations that govern the future behavior of the atmosphere on very big computers. And this is solving a relatively small set of differential equations and physics such as clouds, solar radiation, radiation emitted from the Earth, and turbulence, and their mathematical and physical laws to predict the future state of the atmosphere. So this is exactly what we're doing today as we make these forecasts like Hurricane Sandy. Number 1, it's the satellites, the observations that give us the initial state of the atmosphere. Number 2 is the computer models and the computers that are required to solve these equations on a computer to give the future state of the atmosphere. Well, perhaps the most famous theoretical meteorologist of all times was Ed Lorenz, And I'm told that he's a meteorologist, was a meteorologist at MIT. I'm told he had a big influence on mathematics, the field of mathematics, because he developed a very simple set of differential equations that were nonlinear and showed that from very small differences in initial conditions, differences that were too small to be measured, the future evolution of this system would become chaotic and therefore unpredictable. So no matter how well you observed, the atmospheric analogy is no matter how well you observed the atmosphere, you'd always miss something, and that what you missed would then eventually cause the atmosphere to behave in a way that you could not predict, no matter how good your computer models were. And he estimated from these very simple models that the limits to predictability, which is the potential ability to predict the weather in a deterministic way, was about 2 weeks. And you may have heard for many years that we can't ever expect to forecast individual weather events beyond 2 weeks. That was a surprisingly good prediction. We do have some skill in today's weather prediction out to 2 weeks, but it's not very good. And it's not clear that we're going to go beyond 2 weeks anytime soon. So that's the butterfly effect. The butterfly effect meaning we can't measure every butterfly in Brazil. We can't measure what that butterfly is doing, so therefore there will always be something we don't know about the initial state of the atmosphere, and that will cause any computer model, no matter how good, to lose accuracy, to lose skill in roughly 2 weeks. So I was skeptical, or at least had a somewhat more optimistic point of view in my days at Penn State in the late 1970s. I won't read you the whole thing, but Tom Warner, a student of mine, was developing an early version of a small-scale or regional-scale meteorological model. And we were noticing that this model was appeared to be capable of doing some amazing things. It could predict features that weren't even in the initial conditions, that weren't even observed at the initial time. And the model was somehow creating this information from information that could be observed. And so we hypothesized that in many cases, storms that didn't even exist at the initial time, the formation could be formed, and the subsequent evolution and movement could be forecast. It was kind of an optimistic point of view. So what has happened? In fact, that actually did happen in Hurricane Sandy, as I indicated. The model predicted the formation of Sandy 2 days before it even was formed. Well, this is kind of a complicated chart, but what I want you to notice is the left side is 1981, the right side is 2011. So this is a map of forecast skill from the model that we just heard about that did so well in forecasting Sandy. And these are basically correlation coefficients. So 100 would be a perfect correlation. That would be pretty much at the top of the curve. And then we see 4 sets of curves, all increasing, which means the forecasts are getting better. The top one, the blue envelope, is the 3-day forecast. The next one below that, the red, is the 5-day forecast. The greenish one is the 7-day forecast, and the bottom one, the yellow one, is a 10-day forecast. So what it shows is the 3-day forecast is on the average better than 5 days, which is on the average better than 7 days, which is on the average better than 10 days. The two parts of each envelope are the northern hemisphere and the southern hemisphere. So, for example, the top envelope, the blue ones, the best scores, the northern hemisphere is the top dark blue curve, and the southern hemisphere is the lower lighter blue curve. And what it shows is 1981, the northern hemisphere forecast was much better than the southern hemisphere forecast. But over time, the southern hemisphere forecast has caught up to the northern hemisphere forecast, and by 2011, they're virtually identical. And the same thing happens at day 5, day 7, and day 10. Well, why were the forecasts in the northern hemisphere better, much better than the forecasts in the southern hemisphere in 1981? Not many observations in the southern hemisphere. Much more land, many more people in the northern hemisphere, and only Australia and New Zealand had weather observations in the southern hemisphere. But as time went on, we got more and more satellites which measure the whole Earth, whole atmosphere, and so they measure the southern hemisphere just as well as they measure the northern hemisphere. And so with time, the influence of satellite observations became greater, and the southern hemisphere forecasts have now become just about as good as the northern hemisphere forecast. And that's true of day 5, day 7, and day 15. There are other aspects of this diagram. You might, and that's that the models are getting better in addition to the observations. And one of the ways the models are getting better is in the horizontal resolution. And what these little squares that are going to come up are going to show is the average horizontal resolution of this model at the different times. So in 1981, this is the pixels of the model, if you want to think of them like a camera, were 210 kilometers apart. And what is that feature that's being shown there? You have no idea, right? And wait till you see this as we increase the number of pixels, which means increasing the resolution, and you will see what this turns into. So these are the resolutions as time goes on. In 1984, 125. Still can't really tell what it is. 63 kilometers in 1990. 39 kilometers in whatever that is, 2000. And now you can sort of begin to see what it is. And then by the time you get to 16 kilometers, you can tell what it is, right? It's a tropical storm or hurricane. Now, the very last one is going to be the actual picture of that storm, and these other representations, photographs, if you will, were constructed by just successively removing the pixels, degrading the resolution of the camera, if you will, until the storm was unrecognizable. So, a lot of lessons here. You need good observations, but you also need a lot of pixels in your model. A lot of pixels in your model means a lot of calculations. You need bigger and bigger computers. This shows another way of looking at how realistic computer models have become. The left-hand image is from Meteosat, which is a European satellite showing the evolution of cloud patterns over a day or so, I guess. And on the right, so that's truth. That's what the satellite is seeing. And then on the right is the model forecast of these same cloud systems. And if you look at these many times, you start seeing a lot of features that are the same, that are in common. And so the models are doing a darn good job of representing nature, at least out for a few days. So before Hurricane Sandy, there have, of course, been other major hurricanes. This is Hurricane Katrina. You can see this is a satellite photograph. This is not a model. And it shows the storm moving northward from the central Gulf of Mexico and right over New Orleans. And the photographs from New Orleans, I think many of you have seen. Different city, different kind of bathymetry, different kind of situation, but the devastation was huge. And this storm was also forecast well 3 days in advance, not as far ahead as Sandy was, but it was still forecast pretty well in advance. Now I'm going to show you if this works. It may not work. No, it's not going to work. I'll have to click on this. This is the last one. On the left, actual radar images of Katrina. You can't see it until the storm gets close to the coast because the radars look over the horizon. The right is the model Hurricane Katrina. This is actually a much later generation version of the model that Tom Warner and I worked on in the mid-'70s. It had come a long way through the research of many students in many universities. So let's look at how hurricane forecasting has improved over the ages. This graph goes back to 1970, and in this case, this is the track error, the forecast error by the National Hurricane Center, the official forecast body of the National Weather Service in the U.S. These are Atlantic hurricanes and tropical storms. And on this graph, the graph is forecast error at different times, with the red curve, the lowest curve, being a 24-hour forecast, the next one up being 48-hour forecast, and I can't quite see that. I think that 72-hour forecast is the yellow, and then over on the right, just a short record, is the, 120-hour forecast. So what you see here, in this case, lower is better, smaller errors. 0 is at the bottom, so 0 would be a perfect forecast. And you see the forecast getting better at all these different times, 1 day, 2 days, 3 days, and 4 days. But there's a lot of variation from year to year. Some years the forecasts are better than others, but overall the trends are getting significantly better over the years. And so this is really important. You need to know, you need to restrict the warning area as small as you can so that you don't unduly overwarn a lot of people, and that people get then cynical about the forecast and then refuse to evacuate because there's so many false alarms. So this is very important to get the track prediction correctly. So this raises the question, how much more accurate can hurricane forecasts become? Can they be forecast a month in advance? Month is 30 days, so Lorenz, the butterflies, would say no, that's beyond 2 weeks, so we really can't expect hurricanes to be forecast a month in advance. Well, let's look at a very interesting, not a month in advance, but 5 days in advance, of yet another storm in a different part of the world with a different type of graphics. If you don't want to understand this, you can just kind of look at the colors because they're very beautiful. What you're seeing here is an attempt to depict the flow at different levels in the atmosphere, and the reddish colors are the high-level winds, and the blue colors are the low-level winds, and you'll kind of see what happens as we go through this. But look in the middle of the Indian Ocean. This is I don't have a pointer here, but the Indian subcontinent is on the upper left. The equator is pretty much in the middle of this figure, and Myanmar or Burma is on the is the landmass on the right-hand side. So in the middle of these two jet streams, the pink colors, you see a region of calm winds of blue, very light winds at all levels. As we go into this animation, you will see, as if by magic, a storm, the cyclone that hit Myanmar, form in this region where there is absolutely no trace of the storm at this initial time. So we'll see if this plays. If not, I'll have to go wake it up again. I think you just have to click on it, Lee. Move the cursor on the thing and. Okay, and the point of view kind of moves around looking at things. And so you can see the winds blowing in the northern branch and the southern branch. And right where he left the cursor is kind of close to where this storm forms. But you notice there's just no evidence of it for the first couple of days of this forecast. So this is an example of the large-scale features of the atmosphere somehow forming a very small scale but intense cyclone which wasn't even present in the initial conditions. Now you can see the swirl of the storm, right? And there it is. By magic, it's just appeared in the right place at the right time and moves in the right direction. Well, that's not really supposed to be possible because there were no observations of that storm at the initial time. And yet the model, the equations, produced that storm, and there it is, full hurricane force. You don't have to understand exactly what the colors mean, but you can see a vortex there, right? Everybody can see that. It wasn't there at the beginning. I think that's all, Lee. You don't have to do anything. So I'm going to kind of wrap up here. I'm not going to definitively tell you anything, but about what's really possible. But let me just summarize that there is evidence that greatly improved forecasts of tropical cyclone tracks and intensity are predictable days in advance. We've seen a couple examples. We saw Hurricane Sandy 9.5 days in advance, the Myanmar cyclone 5 days in advance. So we have at least some cases in which this is true. But this is the science part of this talk. Realizing this potential requires high-resolution global models. I've illustrated that. Improved physics in the model, interactive ocean-atmosphere models, improved initial conditions in atmospheric temperature, water vapor, and wind satellite observations, improved data simulation techniques. And you have to have really fast computers to run all this stuff. I also didn't put on here, but it requires scientists putting all this stuff together and making it work. You can do all of these things sequentially or in parallel, and unless some really smart people put it all together, it's not going to mean anything. And so pat yourselves on the back if you're a meteorologist, if you work on understanding of tropical cyclones, if you work on meteorology, if you work on satellite observations, radar observations, and you try to develop and use numerical models. It's hundreds of people like you, largely supported by the feds, because the private sector is not going to invest money with a 50-year payoff, no matter how important it is. It's got to be a public source of funds. It's a public good. It's saving all of our lives and our children's lives. I want to kind of close with a real satellite view of Hurricane Sandy. And just mention that a new satellite program that I've been involved in called Cosmic 2 is under development, which we think will improve the initial observations of all weather systems globally and will produce, in particular, better hurricane forecasts. And so what this will show is the real Hurricane Sandy. Also the number of observation points that this new satellite program called Cosmic 2 will deliver. So you can see the sun go by every once in a while. The picture gets light and then it gets dark again. Here comes the sun. And so this is a several-day period in October, the week period actually. And these dots that pop up and go away are individual atmospheric measurements that are made by this satellite system. So you get an idea of the global coverage and the frequency of these satellites all around the storm, which would feed information into these models and cause the predictions to be better. Again, these are actual. This is the actual 7-day satellite loop of Hurricane Sandy, and you can see it as it moves up the coast of Florida, and then does what no storm had ever done before, and made that left turn very late in the fall, almost wintertime, into New Jersey. And again, very well forecast. Thousands of people had warnings, huge property damage, but relatively few lives lost due to the hurricane. Note that by the time the storm actually made landfall, it had kind of been transformed into sort of a hybrid storm with a lot of extratropical characteristics. That's because a lot of cold air came in from the U.S. But notice the size of that storm, the diameter being, as I say, the biggest Atlantic hurricane that ever has existed. It's a very unusual storm. Cold enough so that much of the precipitation that fell in West Virginia was actually snow. Okay, so in the big picture, who wins? The butterflies or the demon? Well, there's a difference between what is theoretically possible, and that's predictability, and what can actually ever be done, and that's predictions. The demon may be theoretically possible. That's a question for philosophers. Probably a bottle of wine wouldn't hurt the argument. But the butterflies will ultimately win. Meteorology is ultimately going to be unpredictable, whether it's 2 weeks, 3 weeks, 4 weeks, or whatever. But there's no reason not to help the demon a little in such beneficial activities such as weather prediction. So thank you very much. Remind me. Yeah, okay. I don't think so.
No?
Oh, there you go. Yeah.
Okay. Thank you very much. So you didn't really touch on the difference between weather and climate, but there's lots of concern about changing climates. And if we can't predict weather in 2 weeks, what's the prognosis for predicting the climate in 50 years?
Great question. I'm glad you asked that. Climate prediction is not deterministic in the same way weather prediction is. But you can predict climate very well without even a computer model. You can predict that July 5th is going to be hotter and more humid in Ames than April 5th, right? And you know, guess what? That's kind of trivial, but the reason you can do that, and you're predicting the average July 5th. There will be some July 5th that might actually be cooler than on April 5th, but on the average, you can predict very well that climate a year in advance. And that's because climate is forced system. It's not dependent on the initial conditions, the initial observations. It depends on the angle of the sun primarily, and that's an orbital characteristic of the Earth going around the sun. And we know that in July, the northern hemisphere is facing more directly toward the sun than in April and certainly January. So that forcing, that radiation forcing from the sun determines the climate, is the biggest factor that determines our climate. There are other factors too, but climate is a force system, and you're not predicting the weather on July 5th, whether it's going to rain or not. You're predicting that on the average, July 5th is going to be hotter and more humid than April 5th. And you will be right 95% of the time, 99% of the time. If you say June 1st versus May 25th, you'll be right more than often than not, but it's so close, the forcing is so close, you'll won't have as much skill. So that's what climate models are doing. They're forecasting the radiation balance of Earth. And as the radiation balance changes, we can say with some certainty, I think, that with more greenhouse gases, we're going to have a warmer climate. That's pretty sure, and observations show that sea levels rising, oceans are getting warmer, ice is melting all over the world. It's another talk. It's one of my Sigma's eye talks, but yeah, it's a great question, and I hear it all the time. We can't predict the weather beyond 2 weeks. How are we ever going to predict climate 50 years? It's a different system, a different kind of prediction. We're predicting the statistics of weather 50 years from now, not the weather itself.
So what would it take for the European Center to go from a 9.5-day forecast to a 10.5-day forecast with skill? And secondly, what will it take the U.S. to catch up with the ECMWF?
Well, there's been a lot of discussion. The second question is actually probably easier to answer than the first. The European Center, for one thing, has a much faster computer. And they can do more runs at a higher resolution, and they can have better ways of assimilating the data. That's one big reason. It's not the only one. They're also focused on one mission, and that's better global weather predictions. They don't have a lot of other missions like the Weather Service, which has to deal with tornadoes and short-term forecasts and so forth. There's also, I'm sorry to say, a cultural difference. The European Center from the very beginning has been extremely open to new ideas. And they have the best minds from all over Europe coming there for short periods of time, 3 to 5 years, focused on this one goal of being the best model in the world. We have a lot of people, smart people in the U.S., but they don't go to the Weather Service. They don't spend 3 to 5 years focused on that mission. There's not nearly as much fresh blood moving through the system. It's kind of a cultural thing. So those are 3 reasons. Oh, what's it going to take? I hate to say this, but just more of the same. To go from 9.5 days to 10.5 days. Faster computers, better observations, better use of observations, smart people. The same thing that's carried them from 1981 to 2011, going from a forecast now at 7 days is just as good as the forecast was then at 2 days. So that same kind of thing is proven. It's hard work, it's grunt work, but we know how to do it. And unless there's some wildly out-of-the-box thing that nobody's thought of, it's going to be more of the same. Kind of boring, but it's a good model. It's proven. Yes, sir.
There was a claim made, I think, on Clifford Mass's blog that the United States is spending more computational resources on climate change research as opposed to operational weather forecasting. Is this true? If it is, why? And does that make any difference?
Well, it's true. And I think it's terrible that the Weather Service doesn't have more computing power. I think the climate problem is very important, and but we should have a Weather Service that has access to much faster computers than it does have. And that's an immediate importance. So I agree with Cliff. He's got a good point there. I think that, and we're talking about, like, to really upgrade the National Weather Service, something like $100 million, which sounds like a lot. But remember, Sandy was $74 billion. So $100 million over 5 years. That's not that much when you look at the lives saved by these computers. So I think Weather Service should get $100 million for a new computer that would put them up where the European Center is, and they would be making much better forecast.
I've heard it said at mathematical meetings on dynamical systems that in certain sets of conditions, a weather prediction is possible for much longer times than under other conditions. you didn't mention anything about that in your talk. Is that true, and to what extent?
It's true. In some cases, the butterflies don't make much impact. It takes a longer time for the butterflies to make an impact. Some cases are more predictable than others. That's just basically a fact. And mathematically, that means the predictions are less sensitive to unknowns in the initial conditions than in other conditions. And what happens if you're in a situation where there are very strong instabilities in the atmosphere, you have to measure that region very carefully. Otherwise, the instability goes off in one direction, and so it's related to instabilities in the atmosphere. If the atmosphere is kind of quiescent, not a large degree of instability, then the forecast can be better predicted. So there's actually a science of predicting the predictability just from the initial conditions, looking at it and saying this is a more predictable case than another. Sometimes even TV weather forecasts get that this is a really tough thing to forecast, so don't rely too much on my forecast tonight. And that's based in science. Yes, sir. You want to use the mic?
I know that you said that hurricanes aren't really going to be any more predictable than they probably are now, or just a little bit better. But what about the number of possible storms or depressions that become hurricanes? Do you think that would ever be possible to predict, just the number of them per season?
Yeah, I didn't mean to leave the impression that hurricane forecasting is not going to improve. In fact, I think it is going to improve, especially the intensity forecasts in the next 5 years. I see a big room for improvement there. In terms of how many in the next season, I think that's a worthy goal, but that gets into climate prediction using such prediction indicators as El Nino, La Nina, various kinds of oscillations. And that's a tougher problem. I think there's a little bit of skill in predicting the number of storms now, say in April or May for that season, but not a lot. I'm fairly optimistic. I think that there'll be some improvement. I don't know how far that'll go. Thank you.